Hi, this is Taiga Tsukada, PhD student in Hokkaido University, Japan. I will be talking about estimation of the tangential winds and asymmetric structures in typhoon equal region using Himawari-8. This study has already published in GRL as shown here. First, geostationary meteorological satellites seamlessly observe TCs throughout their life cycle without interruption. As a new observation from Himawari-8, typhoon target observation was started. It observes the TCs every 2.5 minutes. By fully utilizing this observation, I think the detailed structure of the TCs will be revealed, and it will lead to an improvement of TC's intensity estimation. This is a movie of the TC's eye. TCs have their maximum velocity at the upper edge of the atmospheric boundary layer in the eye wall. Clouds in the eye are trapped in the atmospheric boundary layer, and it can be captured by the satellite. Winds in the eye can be estimated from cloud motion, and they may be useful to estimate TC's intensity. Therefore, the purpose of this study are to develop a method to derive tangential winds and to clarify the wind structures in the TC inequal region. We chose Super Typhoon Ran 2017 as a test case for method development. This case was also observed by the TPAC2 project with a drop sound. These figures show the track and intensity changes by the RSMC Tokyo best track records. The green hatch indicates the analysis period, which is daytime in local time. We use Himawari-8 typhoon target observation data and JR55 reanalysis and TPAC2 drops on the data. The visible band were used for wind speed estimation, and the infrared band and JR55 were used for parallax correction. Drop sound was used to validate our method. I will now explain the method we developed. First, we collected parallax from the entire Himawari-8 data and determined the TC center every 30 minutes by visual inspection. Its cubic spline determines the TC center every 2.5 minutes. The left figure shows the best track and the derived track. We confirmed the derived track has better accuracy than the best track. Next, the satellite image is projected onto the azimuthal equidistant projection with respect to the TC center and sampled on the polar coordinate. If we derive the tangential wind of a radius of 20 km, fix the radius and cut it along the time axis to obtain an azimuth time cross-section. The slope of the cloud lines on the cross-section corresponds to the tangential wind there. We then divide the method to find the representative slope of this field. We use 2D FFT to decompose the azimuth time cross-section. The 2D FFT reproduces the original cross-section as the sum of these ideal cross-sections with their respective coefficients. This figure shows the computed Fourier coefficients. The right half of the spectrum is counterclockwise components. The relationship between the coordinates and the cross-sections looks like this, respectively. We bring the power spectrum as a function of azimuthal phase velocity and the weighted average of the top 80% beams was defined as the representative wind speed. Spectral peaks due to aliasing of the counterclockwise rotation appear in the clockwise components. So we took them into being as a counterclockwise rotation. We derived the tangential winds using the data over 1 hour every 30 minutes. Left panel shows tangential winds in meter per second. Right panel shows rotational angular velocity in radian per second. The radius is represented by color. H dot shows the actual estimated value, and the solid and broken line is a running mean of 5 samples. The shading denotes the standard error. Inside a 25 km radius, the rotation is close to rigid body rotation, suggesting horizontal mixing. The rotation at a radius of 30 km was faster than the inside, and the rotation in the eye was intensified with time. We verified the results with TPAC2 drop sound observation data. 12 drop sondes were dropped on Typhoon Ram, and 4 of which were dropped into the eye. Note that an exact comparison is not possible, because the drop sonde is a single point measurement, but our method derives asymmetric averaged wind. At the same time and radius, our method showed 25 meter per second, while the drop sonde observation showed 23.2 meter per second. We superimposed each velocity on the azimuth time cross-section, and both are well representative of the wind field. Thus, the comparison with the drop sonde observation was good result. Next, we visualized the asymmetric structures as a deviation from the representative wind obtained by our method. Since the TC is rotating counterclockwise, we rotated the image of TC clockwise according to the rotation speed of a 15-kilometer radius. I'll show you the animation now. Please pay attention to the asymmetric structures. Several metabolites appear in the eye as asymmetric structures. In addition, the straighting clouds are rotating very fast at a radius of 30 km. I hope you can rewind the video and watch it a few times. From the previous animation, a total of 7 metabolites and straighting clouds was seen. The red arrows indicate metabolites and the blue arcs indicate straighting clouds. To estimate vorticity of metabolites, visual cloud tracking was performed by using traceable 3 features. Their vorticities were about the same as the background rotation like this. The red circle shows the location of the metabolites, and the blue circle shows the traced features. We now focus on the straighting clouds. The straighting clouds had a structure similar to the striations or finger-like features, which have been reported several times in previous aircraft observation studies. Visual inspection reveals that the striations were rotating at 1.75 times 10 to minus 3 radians per second. In this figure, the image is rotated clockwise at the obtained speed, and the striations appear to stay in the same place. This indicates that the striations were rotated counterclockwise at that speed. Finally, we discussed why the rotation in the eye has intensified. This figure shows the derived angular velocity and the period of existence of the mesovortices. From it, the vorticity in the eye was increased when the mesovortices were observed. So we suggest that the mesovortices transported angular momentum at the striations inward to intensify the near center rotation. This is a graphical representation of the process. This is a summary slide. We developed a new method to develop the tangential winds in the inner core region from TC target observations. The winds in the eye were generally derived correctly. Asymmetric structures in the eye were visualized and quantified. Visual cloud tracking shows the vorticity of the metabolites has the same order of magnitudes as that of the background rotation in the eye. We quantified the rotation of the striations on the inner edge of the eyeball. We proposed the possibility that the symmetric structure intensified the TC's eye. This result shows the usefulness of geostationary meteorological satellites for TC studies. Recently, a study of inner core wind field in the concentric eyeball replacement using our method has been published in JGR Atmos. Feel free to email me. Thank you.